Hi, I'm Evan, and this is my fixed-wing aircraft project. This build is focused more on design and physics than advanced hardware or software. A lot of the footage you're seeing here shows mock takeoffs, which are used to test stability, tracking, and airflow before attempting full flight. One of the main design choices I made is the wing structure. Each wing was 8 inches in chord and folded over to create a 6-inch airfoil. I added 4 thin foamboard strips inside the wing to hold the airfoil shape. This gave the wings enough rigidity to handle airflow while keeping them lightweight, which you can see during these takeoff runs. The fuselage is 2 inches by 2 inches and about 50 centimeters long. I chose a long, narrow fuselage to reduce drag and improve the straight line stability. The wings are held down with elastic bands instead of glue. This was a deliberate choice to reduce stress on the airframe and allow small movements under load, which is useful during the ground acceleration. It also allowed me to move the wings back and forth after testing during takeoff. Pitch control is achieved using a single servo motor mounted on top of the fuselage, just forward of the tail section. Placing the servo ahead of the tail reduced the mass at the rear of the aircraft, which helped maintain a forward center of gravity and improved overall stability. The servo is connected to the elevator through mechanical linkage. The tail assembly was designed to provide pitch stability and controlled vertical motion while maintaining mechanical simplicity and low mass. The horizontal and vertical stabilizers were constructed from Foamboard and mounted at the same height as the fuselage. This alignment kept the tail surfaces in direct airflow behind the wings, allowing for predictable aerodynamic behavior and consistent control response. A triangular control harness attached to the elevator surface. This triangular shape acted as a lever arm, converting the rotational motion of the servo into linear up and down movement of the elevator. When the servo rotated, the linkage pushed or pulled in the control horn, causing the elevator to deflect upward or downward. This deflection alters the airflow over the horizontal stabilizer, producing a change in lift at the tail and resulting in a change in the aircraft's pitch. I designed and added skis so the plane could operate from the snow. The skis increased surface area, reduced pressure on the snow, and helped the plane track straight during takeoff. The mock takeoff footage shows smooth acceleration and consistent direction, which indicates the ground design is working as intended. The propulsion system uses a brushless motor controlled by an electronic speed controller and powered by a battery. An iFly control on its receiver used to control the elevator and rudder, and the electronics are kept as simple as possible so the focus stayed on the physical design rather than the programming and setup. Environmental conditions ended up playing a major role in this project. It influenced the design changes as well as the time of flight. The bad sequence of rainfall and snow left me with no other day to record a successful or unsuccessful flight. Strong winds combined with the low mass of the aircraft made it very sensitive to gusts, and the weather that day was exceptionally bad. This resulted in a pretty tragic crash. Snow got into the electronics, and the moisture caused the electronic speed controller to short, catching the plane on fire. This burnt through a number of components, as well as some of the internal structuring. Despite the crash, even though the project did not end as planned, the design and testing phases were still successful. The mock takeoffs showed that the aircraft design worked under controlled conditions. This project taught me how important design choices, environmental factors, and testing are in building real aircraft, even at a small scale. Thank you for watching.